let's look at areas of polar regions. Now, I don't have rectangles. We're going to have to do things a little bit differently. So if I start at an angle alpha and I go to an angle beta and I have a function that depends upon what theta is, then suppose I divide this up into n subpartitions and then take the limit as a norm of the partition goes to 0 and add them all up. I wind up with the area as 1/2 the integral from alpha to beta of f of theta d theta. Excuse me, that's f squared d theta. So in general, we just use r. So it's 1/2 the integral from alpha to beta of r squared d theta. Now let's look at an example. Suppose I want to find the area of one petal of r is 3 cosine 3 theta. Now we've already done this problem, and we know that this lower one is minus pi over 6, and the upper one here is pi over 6. You can do any of the petals you want. I just want to do this one because I want to show you something. Okay, area is 1/2 the integral from alpha to beta of r squared d theta. So this is 1/2 the integral. Alpha is negative pi over 6, beta is pi over 6, r squared is 9 cosine squared 3 theta d theta. Now folks, can't integrate that, so you're going to need to use a formula to reduce the power here. So this is 9/2. I'm going to factor that 9 out. It's bugging me. Negative pi over 6. You can leave it in, but I'm not going to. Okay, this becomes 1 plus cosine 6 theta over 2 d theta. Now this I can integrate. And when I do, I get, I'm going to pull this 2 out. This is 9 over 4 times theta plus sine of 6 theta over 6. Evaluate it at negative pi over 6 and pi over 6. You can plug these in, and when you do, you get 3 pi over 4. Now you're going to be tempted, if I wanted to find the area of all three, of course the easiest thing to do right now, so for all three, the easiest thing is just 3 times 3 pi over 4. All right, which is 9 pi over 4. The one thing you cannot do is just integrate from 0 to 2 pi, because if you do that, there's some overlap here and you're going to wind up with an incorrect answer. The other thing we're going to do is find the area between two curves. So say we want between the inner loop and outer loop of this limacon. Well, in order to do this, you need to do a little bit of analysis. When you analyze this, you'll see the inner loop is traced between pi over 6 and 5 pi over 6. So let's look at the area inner. Okay, and that's not going to be included. So we're going to have to subtract this off, but we're going to find it to start with. So this is 1/2 the integral. Now my lower limit is pi over 6. My upper limit is 5 pi over 6. And this is 1 minus 2 sine theta, quantity squared, d theta. This is one of those times when you simply are going to need to multiply it out. Yeah, I'm not going to do all of this integration because you can do it. 1 minus 4 sine theta plus 4 sine squared, all d theta. And when I do this, you're going to need to do a power reducing formula on this again. And when you do this, we find that this whole integration is pi minus 3 root 3 over 2. And I mean, you can do these integrations. Now, what I need to do is find the area of my outer part of my limacon. And when you do that, you see it's going to go from 5 pi over 6 all the way over here. I mean, I could break this up into two integrals, or I could just simply use this as 13 pi over 6, all right? So the area of the outer is 1/2 the integral. Now this time we're going to start at 5 pi over 6, and we're going to end at 13 pi over 6. The same thing. I forgot my 2. Now, if I do that, I see my outer one, and I'm not going to do all of this, is 2 pi plus 3 root 3 over 2. So if I want the area between the inner and the outer loop, the area I'm looking for is the area of the outer minus the area of the inner. So this is 2 pi plus 3 root 3 over 2 minus, let me put parentheses here, pi minus 3 root 3 over 2. And I get an answer of 1 pi is left, 3 root 3